So this is gonna be the video for 4.7 friction. It's actually we're just gonna cover the first part of friction in this video, right? Because I don't want to cover the entire part. Covering the entire friction topic in one video, it's gonna take a long time. It's gonna take like 30 plus minutes. So I'm not gonna do that. I'm just gonna split this into two videos, okay? The dude on question says, well, what do you think happens? What do you think happens? What do you think is the difference between walking on a cement road and walking over ice? And if you look at these two videos, what's gonna happen is you're gonna see a sliding, right? You're gonna see they don't really stick to the road or the ground, and they just kind of slide no matter what they want to do. They can't stop it, right? They slide regardless. And so, what is the difference between walking on cement road and walking over ice? Well, walking over ice, there's less friction than walking on a cement road, and there's more friction on a cement road, so your shoes can do its job. Your shoes are designed so that it creates as much friction as possible between the floor and your shoe, so you don't slip. And so you should probably copy these notes, right? So this is friction. Friction occurs when two surfaces come into contact with one another, and this is only when they come into contact, right? And so friction really isn't just friction. Really, just if you go to the microscopic level of friction, I mean of two surfaces, you'll see that they're not entirely flat. As you can see on the right hand side here, right? If you look at the crate and the ground and look at the magnified image, you will see that it's not entirely flat, right? You see all these valleys, these ridges, right? It's jagged. And while friction is created, well, when these two surfaces rub against each other, these peaks, right? These ridges, they kind of just hit each other, and then you create friction, right? You create heat. The bottom image right here is exaggerated, right? The bottom middle image is exaggerated. It's two surfaces that are very, very not smooth, right? And so when these two surfaces rub against one another, well, you're gonna experience a lot of friction. The GIF on the right shows you friction welding, right? You spin two objects at high velocity, well, you generate a lot of friction, you generate a lot of heat, and then eventually they meld together, right? This is called friction welding. Friction welding. And so friction is always opposite the direction of motion of an object. So, and I want you guys to think about something about friction. I want you guys to think of a situation where you had to move something that was just kind of left sitting there for a while. Like maybe a refrigerator, maybe it could be a closet, it could be a jar, it could be something that's been stuck there for a while, but you haven't moved it, right? And think of like a time. Well, what about the force required? Was it harder to get the object to start moving, right? Or was it, and then it became easier once the object was moving? Or what other situation or what other experiences might you have? Personally, I, I can always tell like, well, it's hard to get an object to start moving because it's kind of like stuck there. It feels like the object is stuck there, but once I get it moving, it takes a lot less force to keep it moving, right? And so that this is the situation I'm talking. I'm sure if you've ever had to move an object, maybe you've experienced this. Also in school, you kind of experience this with tables, right? If you ever try to move a table or chair, you probably experience this. So this is actually a phenomenon. This is a real phenomenon. There are two types of friction. One type of friction is called static friction, and the other type of friction is called kinetic friction. So I'm gonna let you guys copy the notes here, right? This is very important. So these are the notes that you should copy. And you can see in the GIF, right? You can see in the GIF. Let's look at the top part of this GIF. Let's look at the top part. You can see that, well, the man is exerting a force of around 35 newtons, right? But once you cross that threshold, once you cross 35 newtons and get the object to start moving, well, you don't really need as much force to keep it moving anymore. as indicated on the bottom portion of the GIF, right? So once the block starts moving, well, the amount of force required is somewhere around 28 newtons. And again, this is a scale, measures force, right? So it's kind of what you see. All right. So again, you guys are going to copy this. Let's get a look at this. Anyway, if you're doing the friction lab, if you did a friction lab on Monday, you see that, right? You saw that in your lab, in your graphs. So let's take a look at this, right? So now you have speed. And there's something here I want you to notice, right? So you're applying a force. Let's say apply, and something I want you to notice between the applied force and the friction force. And what I want you to notice is that, well, no matter how much force I apply, my frictional force is equal to the applied force. And right now, this friction force, we're going to call it static friction, right? Because static friction is a force that is experienced when an object is at rest. And once you get the object to start moving, well, we call that kinetic friction. And the kinetic friction is always less than the maximum static friction experienced. And you need less force to keep it moving. So going back to this, let's say I apply a force of 160 newtons, and so that means there's a static frictional force of 160 newtons in the opposite direction, right? Because if the object is at rest, we're going to call that static friction, or we're going to call this static friction because the object is at rest. So, and then there exists a threshold, right? A maximum static frictional force, and in this case, it's actually over 250. So if you go over 250, if you apply a force over 250 newtons, well, you're going to get the object to start moving, right? And I want you to take a look at the number for frictional force. Right, so that's your static friction force, and we must overcome this static frictional force to get the object to start moving. So let's apply a force of 251 newtons now, so over 250. And so now the object starts moving, and I want you guys to notice something. So now this friction, we call this kinetic friction. Well, what do you guys notice about your frictional force? Well, once it turned into kinetic friction, well, now you see that your frictional force is less. Your kinetic friction is less than your static friction. It's now 188. And what I can do is I can actually lower the applied force now. I don't need as much force to keep the object moving anymore. I can lower my applied force and the object will still move. I don't have to do anything, right? I can lower the amount of force I need to get this object to start moving, to keep moving rather. And therein demonstrates the difference between static and kinetic friction. You need a greater force to get an object to move, whereas once it's moving, you don't need to apply as much force anymore, right? Because in the beginning, we needed to apply a force greater than 250. We need to apply a force greater than 250 to even get it moving. But once we cross this threshold, well, we can now reduce the amount of force we need to kind of keep the object in motion. So we don't need as much force anymore. We can lower the amount of force we require. All right. Now these are the friction formulas. So I'm introducing you to the coefficient of friction. So that's that U, right? That's that U here. F sub F, your force due to friction, is equal to mu. We're going to call that mu Fn. Right, and so that's your normal force. And so your coefficient of friction describes the degree to which friction is felt between two contacting surfaces. Take, for example, the man running. Right, the man running clearly has more friction between the shoe and the floor, whereas, well, the dog's paw doesn't have as much friction. And so we can say that there's a higher coefficient of friction here between the shoe and the floor versus the dog's paw and the floor. And these are two static frictional formulas and the kinetic friction. And so now we get to the first question, right? So for an object moving along a path. So again, we kind of have this. I have this. So in the friction formula, you should have seen that, well, you have your force due to friction is equal to mu Fn, and mu is something you can just get from our reference table where we solve for it. But what is Fn equal to, right? What is Fn equal to? Well, if you remember this GIF to the right-hand side here, you'll see that, well, I showed you this in equilibrium, right? And the topic we covered by equilibrium, I showed you this. And so Fn is equal to something. If you take a look here, if your net force in the y direction, if your net force in the y direction is equal to 0, well then, well, your total force is acting in the y direction if you're not moving up or down. So the total amount of forces acting in the y direction is, in both cases, Fg and Fn. Well, what are the forces acting in the y direction? Well, it's just Fn and Fg. And so now we have my net force is sum of all my forces, right? This is something you should have learned in the previous topics. So Fn is the sum of my forces. So my only forces acting in the y direction are Fn and Fg. So Fn is equal to Fn minus Fg is equal to 0. I'm minus Fg is negative because, well, it's a downward force. It's acting in the opposite direction. And if I were to solve for Fn, I would get Fn is equal to Fg, right? And so now we solve for what Fn is. Fn is equal to Fg. Now, if you don't want to remember it, if you don't want to remember the proof, well, the only thing you actually need to remember is that Fn is equal to Fg. And well, what is Fg equal to? Fg is on your reference table. On your reference table, it says G is equal to Fg over M. Well, if we solve for Fg here, if we multiply by M on both sides, we get Mg is equal to Fg. And so now we can posit the situation. So Fn is equal to Fg is equal to Mg, where M is your mass and G is your magnitude of the acceleration due to gravity, which is 9.8 meters per second squared. Right? And so that's what Fn is equal to. And if you don't want to remember the proof, well, you just need to remember this. So let's do the final part of this video. We're gonna do a practice question. Right? So this is the final part of the video. So you have a rubber block weighing 100 newtons. Right? So weighing 100 newtons, well, that's gonna be your force due to gravity, right? Well, this is your weight. Your force due to gravity is your weight. So Fg is equal to 100 newtons. So Fg is 100 newtons. And it's resting on a horizontal surface of dry asphalt. Well, the resting part is not too important. Actually, it does tell you one thing, though. That you're dealing with static friction. The object has not moved yet. And so if we're dealing with friction problems, well, we're dealing with static friction here because it is resting, right? It hasn't moved yet. Only when the object has moved are we dealing with kinetic friction, but the object has not moved yet, right? It's at rest. And so here we're dealing with static friction. And then you have a rubber block on a horizontal surface of dry asphalt. So you have a rubber block on dry asphalt. And if you take a look here to your right, this is on your reference table. This is your coefficient of frictions. Coefficients of friction. And your coefficients of friction, again, they describe, well, to what degree of friction is felt between two surfaces, right? So clearly, if you're rubber on asphalt, on a dry asphalt, well, you have more friction than if you were driving on wet asphalt, right? There'd be less friction. And there's even less friction if you're driving on ice, right? You have even less friction there. Right, so they describe the degree which friction is felt. And so we can say that since we're dealing with static friction here, and we have a rubber on dry asphalt, we can say that, well, my static coefficient of friction, we're going to call that US, my coefficient of static friction is 0.85. Now the question goes on to say, well, what is the magnitude of the minimum force needed to start the rubber block moving across the dry asphalt? Think back to your lab on Monday. Think back to the simulation. Your applied force, and again, this question is looking for your applied force, right? They're looking, well, what is the minimum force needed? What is my applied force I need? Well, if we go back to the simulation, you'll realize that, well, your applied force U is always equal to your static frictional force. And there's a maximum static frictional force you must overcome, which is what this question is asking. They're asking, well, what is the applied force necessary to overcome your maximum static frictional force? And so you know that your applied force is always equal to your static frictional force. So they are looking for, even though they are looking for your applied force, we know that my applied force is equal to my static frictional force. And so we're solving for our frictional force here. If that was too difficult for you to understand, the only thing you actually need to remember is that if you're dealing with friction problems, and they're asking you what's the magnitude of the minimum force required, well, they're always going to be looking for Fs. Okay, they're always going to be looking for Fs. So we have a formula here, Fs, we have the friction formula. Your force due to friction is equal to your coefficient of friction times your normal force. Well, what's my normal force here? Well, we covered that in the last slide. My normal force, and this is something you just have to remember even if you don't understand the proof, is that Fn is equal to Fg. Right? And so we have mu is equal to Fg. So mu is 0.85 and Fg is 100. And so we solve this and then we get 85 newtons. So this is my force due to friction. This is the amount of force I need, right? This is the amount of force I need to overcome the static frictional force to get the object to move. All right, that's the end of this first part of friction. The more stuff will be covered in the second part of the friction video.